Welcome to today's Explainer. Today, we are putting on our systems architect hats to deconstruct the universe itself. We're going to look at reality not as some random collection of objects, but as a highly precise, self-regulating mechanism. We're diving deep into the Nexus 4 framework. This framework proposes that literally everything, from physical matter to computational networks to biology, operates on a universal blueprint balancing expansion and resistance. By the time we're done here, we are going to fundamentally rewire how you look at growth, pressure, and the very nature of information. Okay, let's dive straight into this blueprint. We'll be breaking things down into 5 parts today: the engine of emergence, the structural load, systemic failure modes, the cybernetic patch, and finally, the ultimate epistemology.
But before we get to any of the metaphors, I want to ground this in strict mathematical rigor. The Nexus framework is not just generative philosophy, It's a verifiable structural reality. The underlying math boasts 0 structural violations across 348,508 prime pairs. That proves we aren't just tossing around abstract ideas today. We're looking at hard, structurally verified reality that scales all the way from prime numbers up to living ecosystems.
Act 1. The engine of emergence. So, to understand any system at all, we first have to establish its core baseline function. In this framework, that function is radial expansion, but we call it blooming, because it's not just moving in a straight line from point A to point B. Think of a flower bud. Blooming is an in-place release of potential energy. It's exposing more relational faces and expanding outward from a single point of origin, all to seek equilibrium. And this brilliantly illustrates just how universal this thermodynamic drive really is. Whether we're talking about physics, chemistry, or biology, the underlying mechanism of radial blooming is identical. Take water ripples, right? A disturbance transfers kinetic energy, causing molecular oscillation that blooms outward. Or look at blast waves, where chemical energy from a detonation creates a supersonic expansion of high-pressure gas. We even see it in biological cellular growth, specifically in the microscopic green alga coleochate. Its marginal cells use metabolic energy, specifically turgor pressure, to physically drive the viscous deformation of its cell walls. It's amazing. Kinetic ripples, explosive shockwaves, and biological cell division are all executing the exact same architectural code: radial energy dissipation from a point of origin. Act 2. The structural load. Now, a system obviously can't just bloom infinitely into a void. For it to have stability and actual form, there has to be a compulsory counterforce. We define this as pressure. And in our system's architecture lexicon, pressure isn't just a physical weight, it's a universal gradient. It's the environmental load or the homeostasis that actively sculpts, constrains, and forces that bloom to adapt. A system in perfect equilibrium? Well, that system is dead. It's the pressure gradient, the difference in physical quantities over distance, that creates disequilibrium and drives spontaneous flow and evolutionary design. To see this in action, we just have to look at how biology engineers structural patches to withstand catastrophic pressure. Consider deep-sea organisms, known as piezophiles. These guys live under a crushing hydrostatic load. To prevent their internal systems from just completely collapsing, they deploy some truly incredible physiological adaptations. For instance, they accumulate a molecule called TMAO, which acts as a structural anchor for water molecules so their proteins don't get crushed. They literally alter their protein structure to have fewer internal cavities, meaning high-pressure water can't force its way in and unfold the molecule. They even increase their cellular membrane fluidity using unsaturated fatty acids with structural kinks, basically so their membranes don't freeze solid. This is pressure acting as a profoundly creative architectural force. Act 3. Systemic failure modes. But what happens when that pressure just isn't enough to contain the bloom? Let me pause here and ask you a direct diagnostic question as we analyze this architecture. What happens when a self-amplifying process lacks a terminating condition? If a recursive loop just keeps running and running, expanding without any structural limits to stop it, what's the inevitable result?
The answer is a stack overflow. In computer science, this is an inherent architectural error where a program entirely exhausts its finite memory allocated to the call stack, usually caused by infinitely deep recursion. The system essentially engages in a self-amplifying process, gobbles up all available resources, and completely crashes. And let's see how this builds a bridge directly into biology. The computational failure of a stack overflow maps perfectly onto natural ecosystems. On the coding side, infinite recursion exhausts memory. On the natural system side, a biological species overshoots its environmental carrying capacity. Organisms absolutely have the potential for exponential population growth, but when they exceed finite resources like food or habitat, the ecosystem experiences a natural crash. It is the exact same deterministic failure mode playing out across two completely different substrates.
Act 4. The cybernetic patch.
So how does a complex system actually survive and avoid this deterministic crash? Well, first we have to understand emergence. Think about cellular automata, like John Conway's Game of Life. You don't need complex components to build a complex system. You just need simple, local rules interacting on a grid. As time steps forward, infinite emergent complexity arises, whether it's gliders moving across a grid or the infinite cell similarity we see in fractal geometry. It's beautiful. But simple rules alone still can't stop a stack overflow.
So here is the crucial point. The system needs to become self-aware. This is called second-order cybernetics. A basic first-order system just runs its code until it hits a wall and crashes. But a second-order system has the capacity for self-reflection. It can observe its own states and actively modify its own rules. In biology, we call this autopoiesis, living systems producing and maintaining their own organization. This self-reflection is the ultimate cybernetic patch. It allows the system to safely rewrite its own operating rules on the fly to avoid hitting the wall of a stack overflow.
Act 5. The ultimate epistemology.
If reality really is this highly structured, cybernetic architecture, how does it process absolute truth? Well, let's look at the paradox of pi. Pi is simply the geometric ratio of a circle's circumference to its diameter. It's an incredibly simple, perfect, unchanging rule. Yet somehow, it generates an infinitely complex, transcendental, non-repeating cascade of data. It completely proves that within structural frameworks, perfect simplicity is the ultimate engine of staggering complexity.
And this gives us two distinct ways to process information in our universe. On one hand, we have active computation. This is science, the scientific method, modern artificial intelligence. AI isn't born with knowledge, right? It's a noisy, continuous process of adjusting parameters using things like reinforcement learning with human feedback. It's a massive, distributed feedback loop. But on the other hand, we have silent truth. This is the ultimate cosmic lookup table. It's a static, complete repository of absolute truth, where answers aren't computed through noisy feedback at all. They're simply retrieved. Truth in this framework is totally silent.
We'll wrap up our explainer today with this really profound quote directly from the Nexus texts. The primitive is not value. It is gap pressure against transformation capacity. I want you to really think about that. Numbers, values, metrics, they're just shadows. The only thing that is truly real in this universe is the relational pressure a system places on your capacity to change and adapt. So, I leave you with this question to ponder. When you inevitably hit the structural limits of your own environment, will you crash like a stack overflow, or will you use self-reflection to rewrite your own rules? Thanks for exploring this incredible framework with me today. Keep questioning the architecture around you.